Good afternoon, class. In today's video, what I wanted to do was to talk about an example of how lenses work. So in the last video, when I introduced more of the vocabulary of how lenses work, what I should go into a little bit more is a little bit of the setup of how we do these thin lens problems. This will lead us into the mathematical setup for when we do the equations of the thin lens equation. But for this one, just to think about how to picture everything, especially when you're doing a ray diagram, it would look something like this. So let's say I've drawn a picture of a tree, and feel free to make comments about my artistic abilities. I know they're not the greatest, but that's okay. That's why I'm a physics teacher. So I drew a tree, and what I did was I took the image of the tree and I sent it through the lens and had it do its thing, whether it's concave or convex. I had it bend the way that it was going to refract, the way it was going to refract. And so what happened was, when it goes through the convex lens, it bends down like this. So this, and again, this line right here, this or should I say this light beam is actually the top of the tree. So when it goes through and to the bottom, what will happen is that the top of the tree is down here. Now, there are a couple of things that we should note. This direction is positive. Whenever we do a ray diagram, going from left to right is positive. If anything goes from right to left, it is negative. So the object is always going to be on the right-hand side, or on the left-hand side, sorry. And the image should always be on the right-hand side, because the light should move from left to right. If it goes the other way, that's a problem. Or at least in terms of it being positive. That just means that the image distance will be, or the image distance will be negative. So I want to make sure that that's clear, because that's what our conventions are going to be. Especially, you'll see that when we actually do the formulation for it. And what I'll do in this video is I will demonstrate, using some of my lenses, what the actual properties are of the converging and diverging, or a convex and a concave lens. And then in the next one, we'll formulate and see why, when we do using the thin lens equation, why those signs matter, whether it's positive or negative. So we'll go over those. But so for this one, what will happen is I've drawn this black line as what I call the optical center, meaning that's the place where I'm just going to rest my image, and that's where you'll generally see that in most ray diagrams. So then what happens is I draw another line that goes straight through this lens, and the reason why it goes straight through is because at least according to the traditional rules of drawing a ray diagram, there are usually three lines. One will go down at the bottom of the lens, one will hit the top of the lens, and the other will go straight through the lens, because that's where all of the normals align for this lens, and it goes right through. I know in the last video you saw me having the straight line going through. That was a special case of when the light comes from infinity, or when all the rays are parallel. Then when they hit the lens, they'll do that converging thing in the convex, or the diverging thing, or the diverging bend when it hits a concave lens. The middle line will always stay the same. However, we're talking, when in this case what we're doing is we're taking a look at what happens when we're just talking about a certain portion of this image. In this case, it's the top of the tree. Where does the top of the tree go? Is it above the center line, so it would have a positive height, or is it below the center line, so it'll have a negative height? And that's why you'll see the top of the tree gets projected over here. And so that means it's inverted. That's why a real image is inverted, and it's generally smaller, but that's not always the case. It depends, of course, how far away the object distance is, the focal length of the lens is itself, and of course that will all determine where the image is and whether it's real, virtual, inverted or not inverted, and how big the image will actually be, and I'll actually show that in a few minutes. Same thing with the concave lens, except that because the light is diverging, what will happen is that the image has to track backwards through the lens, so that the image distance will actually be negative, because it's going the image is being projected to the left of the lens, whereas a positive distance for an image to be written is to the right of the lens. So because it's to the left, it's a negative image distance. But of course, as you noticed, when I projected it back, this top line to show the top of the tree, it gets projected above the center line. So therefore, for the concave lens, the image is upright. But because it's behind, or because the image distance is negative, it is virtual. So that's what will happen. Now, of course, I could draw this all day long, and you could probably argue with me about whether you think that I drew this correctly. Maybe you think that these drawings are not representative of anything because, I'm not that great as an artist. So that's a fair point. It would be much better, of course, if we had actual examples, which is why I brought a couple of my lenses that I have for demonstration purposes. So what I'll do is I'll show you this lens, and I'm going to be showing this tree because I drew it the biggest, so it's easiest to see. Now, I'll give you a hint. This is a diverging lens. Now, you may not be able to see it from over here, but as I bring it closer, what you're starting to see is that everything in here is upright. So that means all of the images that are coming through this lens are virtual. So what you're seeing right now is a virtual image. It's upright and magnified. So that's why, like I said in the last video, that would make this a diverging lens. And so you can use this to see that like you can see right now, my eye is upright. So that means it's a virtual image. With a converging lenses are a little bit different story, however, because when you've got a converging lens like this, you can tell because, as I'm trying to get this correct, you can see that the image of this tree, back go the other way, and sorry, I apologize, this is all kind of mirrored for me, so I think it should go this way when I really should be going this way. So as you can see, the tree is upside down. However, if I'm using this one right here, which is right side up. So this is not, so that's why this lens is converging, because the image through this is inverted. Now, of course, how can you tell if it is projected? If I can project that onto a screen, I'd actually have to have a light source travel through it to actually see that example. But I want to point out one other thing. As you can see, this is a real image. It's inverted, and there's a magnification. However, as I bring it in, I want to make sure I keep myself on that on the image here. Sorry if this is taking a little bit longer, but I wanted to bring this in as close as I can. Okay, as you can see, it's getting a little bit more out of focus, but it's still real. It's still a real image. And as I bring it closer, it starts to flip around, and all of a sudden, it's right side up again. What I wanted to point out in this case is that now what you're seeing is a virtual image because the image is right side up. So with that, and the reason what you can actually tell from this is actually the focal length of this lens. You can even do that with my eye. I believe you can see it from here. There's my eye. Oops, right there. It's upside down. But then if I bring this closer, my eye is right side up. So this is an example of a converging lens. Every lens will have a focal length, and you can actually discover what the focal length is by measuring, taking parallel beams of light. So like, for example, the lights above me are far enough away that they're parallel, and then wherever you see the image projected, that's the focal length of the lens. The whole reason that that's important is because if you go if you go in front of the focal length, if the image distance is in front of the focal length, then what happens is that, if the object distance is in front of the focal length, and the focal length is greater than the object distance, the image distance is going to be negative, which makes it virtual. So I want to make sure that that is is clear, and hopefully that demonstration kind of helped you understand what how these lenses work. So in the next video, what I'll do is I'm going to go over the thin lens equation and how you actually get mathematically all of these examples that you just saw in this video. So good luck in your studies, and may the force be with you.